Hello.
Hi Rohit. Give me 1 minute. I'll share my screen. Okay. Let me share my screen now. Fine. I started my sharing. Let me just run all of the cells quickly so that we can start from where we had left off. And then in the meanwhile, let me just quickly correct what we or what I did as a mistake yesterday. So if you look at the statement here, the sales are in thousands of units and the budget is in thousands of dollars. Okay, so that means that X is in the scale of thousands of dollars. Okay, and then Y is in the scale of thousands of units. Okay, so what we found out, let me clear this because there's some problem with my mouse. Let me just write over here. So Y is equal to, it was something like 6.55 if I'm not wrong, plus 0.055x. This was our expression, right? So that means that for every 1 unit of X, there is this much value for Y. So, right? So 6.55 plus 0.55. This is like 6.6. Okay, 6.65, right? So yes, 6.65. So I can say that for x equal to 1, y is equal to 6.65. Now this means that 1 can now be represented as, I'll just move this a little bit so that we can see over here. X is in the budget, which is in thousands of dollars. So I have to clearly say X being 1 means $1,000, right? So $1,000 of investments in TV will yield into 6.65 multiplied by 1,000. So that will be 6,650 units, right? So this was the estimation. So I believe I have written 7,000. We can change it over to 6,650 units. But I was considering this as 1 unit, which is wrong, right? So this is like thousands of units. So that's the expectation. So let me just clear all the drawings and let me see if it has executed. Yes. So 650. Okay. So this is my finding from this analysis that we have done. And just to recap, what are we going to look for when we are going to do this kind of the analysis? First of all, we look at R squared. Okay, this being closer to or the adjusted R squared. So this being closer to 1 means a very good model. If it is not closer to 1, there is something wrong. Okay, as simple as that sounds. The second thing I will look into AIC and BIC, we will cover at later stage. We will look at this. Okay. We may look into F statistic, but there is no point because we don't know the critical value. Okay. But if we look at the probability value, we can clearly see this is very, very small, which means our assumption was right that we have a linear, obviously we have a linear relationship, but it changes the way or it affects the way the output variable is going to regress, right? So y is really regressed by means of x. Okay, that's what we have found out over here. Okay, so that's a good thing, and that you can clearly see over here as well. Let me just scroll down and let me clear all the drawings. Uh, Hi Saranksha, I hope you can hear us, right?
Yes, Somik. Now I can.
Okay, yeah. So we have two constants. Okay, first of all, the constant has changed. So maybe I'll have to take this into account. My calculation is wrong. I'll update that. So the constant is 6.97. This is my beta zero. This is the intercept. So if I draw a graph like this, it's something like this. Okay, so this point over here, this point over here is 6.9748. Okay, and then the coefficient for tv is my x, right? So tv is here, tv is my x-axis. So the coefficient for tv is 0.055. So this is beta 1. Okay, this cannot be represented here because it is not the, it is the slope. So it is like this. So if I take this angle and take a tangent of this angle, the tangent of that angle is 0.055. Okay, but irrespective of that, if you see the standard error, the values of these errors are very less, which is very good. It's an indication that our test has been done without much of an error in them. But usually there will be errors in the tests. Okay, so there wouldn't be scenarios where you will not have errors in the test, right? So that's the first thing we always need to remember. There will be errors in the test. Okay, because those values are not going to be so good as we see over here, right? So that's one thing to look for. Then moving on, we will look into this p-value. P-value very close to 0, and obviously p should be less than my alpha value, which in this case I did not specify, right? I have not defined that I would like to be 95% confident or 99% confident and so on. So because it is not specified, obviously my level of significance or alpha value becomes 0.05, and p should be less than 0.05 to make this feature a good feature. Why I'm stressing on this line is because when you have multiple linear regressions, right, or use cases like that, you will see, and we can even fit a multiple linear regression with this context only, with this data, because I have at least 3 channels of advertisement and I'm trying to compare the sales, right, which is my target variable. So I've taken deliberately one of them basis the EDA that I've done, right? So I've taken one of them deliberately, but I can also take the rest of them, in which case what will happen is this part, right, is going to look something like this. You'll have a constant, then you'll have x1, then you'll have the next x, then you'll have the next x. So x1, x2, x3 will be your 3 independent variables, and for each of them you will get the coefficient, for each of them you get the standard error, for each of them you get the p-value, for each of them you get the t-test output, right? Now that's the main thing that I'm going to look at. While these values over here, which you see over here, are even more statistical tests which are performed on the data, we can look into them later on. These are not really that important, but what I mean by here is, let's say x1 has a p-value which is very close to 0, but x2 has a p-value which is like 1, and x3 has a p-value which is also very close to 0. This means x1 and x3, these two independent variables, are actually contributing to the regression for y. Okay, so for y to regress, x1 and x3 are good contributors, because in that case our hypothesis or our null hypothesis is getting rejected, right? That's the way in case of multiple linear regression, which we will see if we have time today. We are going to see today, or we are going to see in the next class. So in that case, we can find out what is the most relevant x for which y is going to regress, right? So that is also a method which we can mathematically prove now. Earlier assumptions were our basis, the coefficient, and let's say the correlation, the graphs, and so on. Now we can also statistically be confident that yes, what our assumptions were, they are actually correct, and that tv is really the best predictor for sales, which I can write it down. So our model states, for every USD $1,000 spent on TV advertisement. Why I'm writing USD here is because, friends, dollar sign has a different meaning in case of Jupyter Notebook. That's why I have deliberately written USD. Okay, so per or for each $1,000 of spend on TV advertisement, we will see a rough sale of 6650. This number is wrong because you have to calculate again. 6.97 plus 0.05. Let me just bring out my calculator. You may not be able to see it on my screen, but let me just be very specific here. So it's let's say Just a moment. So yeah, 6.97. No, why do I need a calculator? I'm already inside Python, right? Shit. 6.97 plus 0.055. Okay, what is going to be the value? 7.024. Okay, 6.9748 and 0.0555. Okay, now I take this value and I multiply this. Let's say uh, I have to put a bracket over here, and I take a multiplication sign here and say 1000, and I do a shift enter. 7030.3. So approximately I can say 7030. Okay, so 7030 quantity, okay, of my items will be sold for each $1000 investment on TV advertisement. So this is really good. Now what happens is, why this equation is really useful is because why this equation is useful is because I can even write the equation. So this note, this is basis the regression equation given by or given as sales, sorry, let me just do this like this. Sales is equal to 6.9748 plus 0.0555 multiplied by TV, right? Now, why is this useful is because, example given, if we have $200 of or 200 USD, okay, USD 200 budget for TV advertisements, right? Then what will be the sale? Okay, divide this by 1000, it becomes 7.03. Multiply this. So you divide this by 1000 means you don't have to write this. Okay, you don't have to write this. Divide this by 1000, and then you get this. And then all you need to do is to multiply this by 200. So what you do, I'll just realize that I made a mistake. I could have just done this. Okay, so you simply multiply by 200 and you get 1406, right? So then we expect a sale of 1406 items. Okay, 1406 items, right, of my product, right? Okay, so this is my model output. Okay, this is the output that we have got. Okay, this is how to interpret them. So this is what we are going to write in the final analysis. One quick tip from my side. This is basis my experience. If I'm going to present this to my client, let's say Saransh is my client and I'm actually presenting this to him, I'm going to create a PPT. And the first thing that I write in that PPT is this, or the first slide, or maybe the second or third slide, which I'm going to put in that PPT, right, is going to be this. Okay, please remember this. Don't bore your people with what you're going to show them at a later stage. Please be very specific, right? Please be very, very specific and show them or tell them the answer upfront. Okay, once you have told them the answer, then you elaborate. Okay, so maybe if you are going to create a presentation, the first slide may be the introduction, the use case, and all these things, things that we have written in the first section here, right, in the problem statement. And then you directly jump down. You don't show them any graph, you don't show them any EDA, directly jump down to this model, your best and final model. Okay, and then you simply show them, okay boss, this is what we have done, this is what we have found out, and this is the best statistical model that is available with the data that we have. Okay, that is the first suggestion I would give, which is a practical kind of thing that you should do. The second thing I would suggest is that never create a model on the population data. Okay, irrespective of the fact that how much small your sample might be. It may well be the case, okay, it may very well be the case that you have a sample which is very, very small, or a population, I'm sorry, a population which is very small. Okay, a very small population you have, and you can clearly take all the data, right? You can clearly take all the data and you can do all the analysis that you can do, and then you can show the data all good. Please don't do that. Always take a representative sample. Okay, always take a representative sample, always. Okay, please don't do your analysis Okay, please don't do your analysis on the population data, howsoever small it might be. Try to avoid that. Okay, try to always take the sample of the data, then you do this thing. So imagine this advertisement.csv file is actually a sample. Okay, it is not the population, not the entire data. It may well be, let's say, randomly chosen dates from 200 months. Okay, we had 200 entries, right, in the data. Okay, or maybe randomly chosen 200 entries from 200 different weeks, or 200 consecutive weeks, or one random day from each week for the last 200 weeks. Okay, that's how you can try to imagine that I have sampled the data. Maybe my business is running for I don't know, 6 years, and now I'm interested to know what kind of advertisement media is best. Okay, so that's the way I would like to suggest you. But this is not the end of the game. This is just the beginning. Okay, let me tell you why this is the beginning. You have created the model. We have done the initial modeling. Okay, we have found out what is the R square value, and we have found out all the P values and so on. We have found out the equation. What we have not done is we are yet to validate if my assumptions are correct or not. Let's validate the assumptions first. Then we are going to call this model a good model. Okay. So what we are going to call the next section is 3 dot. I think this will be 3, right? The modeling section was 2. No, it was 3. So this is 4. So I'm going to call this residual analysis, right? Before we even move ahead, I know a very quick question you may have is, if on the first slide only I'm going to show the output, then what is the meaning of me creating this IPython notebook, right? This IPython notebook goes into your appendix, okay, or on the last page of the PPT file. Okay, it is, you can clearly mention that in the heading of the PPT. You can say, for any nerds or for people who would actually like to look into the code, please open this file. I've already attached it here. The data set is also there. You can download the data set from so and so URL, open the notebook, and you can look into the code that I have written. You can also look into the data set using any other statistical software, right? Don't show all the analysis to the customer. Show the visualizations. More focus on the solution and the visualization. Now, to look into the residual analysis, what we need to do over here? What we are doing over here is that we have our first model. We will now validate how good or bad our model is. One quick way above was to check the R squared value, which is really good. Okay, because it is like 0.82 something, right, which is really good. The other aspect to look for is to validate the assumptions of linear regression. Okay, to validate the assumptions of linear regression, right? We had 4 assumptions. If you remember, we had 4 assumptions. Let me just quickly go back and find out where are the 4 assumptions. Here, there is a linear relationship between x and y. We have already seen this using our graphs, right? And then we have already proved that it is there statistically as well. Error terms are normally distributed. So I have to find out the residuals and I have to see the distribution of the residuals, right? Right? Now, point number C and point number D is a little difficult to find out, and we can even or we can even try to justify them. Okay, so that is the reason why what we are going to do is that we are going to take them together. Okay, we are going to take them into one step, I will say, and we are going to look for patterns. Okay, if we look for patterns in the residuals or in the errors, then we are going to answer whether we have homoscedasticity or not, right? So that we can answer. But before we go in there, I can quickly write my findings over here, or maybe before I just to save time, right? Before I share this file with you, I will write my best practices here, right? So let's go back here and let's try to visualize the residuals, right? So clearly, I need a prediction. Have I got the prediction? The answer is yes. If you remember, we have done the prediction earlier. Y underscore pred is equal to my model dot predict function. I have passed on the x value, right? I have passed on the x value. So now I need to find out the residuals. find the residuals. Okay, what is the residual? The finding that I have done, or the prediction that I have done, minus or the actual value, okay, minus the predicted value. Okay, so actual value minus predicted value is my residual, right? So I'm going to call this res. Okay, let's say I'm going to call this res. So what is the actual value? Actual value is what? Y, right? Y is the series that contains my actual values. And predicted value is what? I have just predicted it over here. I have written it as y underscore pred, y underscore PRED. So this is my residual. Simple as it sounds. If I print this, I'm going to get the residuals. Okay, this value 2.36 is basically the difference between the first row of y and first row of my pred. Right now, I don't need a table. I need to visualize this properly. Visualize the residuals. How am I going to do this? Let's say I'm going to do SNS dot dist plot. Okay, this is one way in which you can look at the distribution. We could have used a plt dot hist as well, because that also gives you a good histogram. But if you remember, Seaborn's dist plot function gives you that smoothened line as well, right? So I'm going to take that and say, give it input as a residual, and maybe I'm going to also select the bin as I don't know, randomly 15. Okay, I can change that value later on. Let's see how it is going. Right now, I'm going to call this plt.x label. Right, I want to give the labels to x. So I'm just going to give the label to x as y actual minus y predicted. Okay, just kind of a mathematical name, right? One thing I wanted to tell you is that you can even give the size of font for the label. So let's say if I give 10, we'll see how it goes. Or maybe I will give it, let's say a 15, and let's see how it goes. If I want to increase or decrease, I can do that. Okay. I can also give heading. And to do the heading for any visualization, I can use a function called PLT, or I can even do something like this. I can create an object called figure, which is plt.figure. This creates an object for this figure that I want to draw. And here, before I do the labeling, I can say fig.suptitle, super title, okay? Or the title of the graph is error terms, right? In this case, I'm trying to do the error terms. I'm also going to say font size is equal to 15, let's say. Okay, finally, let's not waste time, plt.show. So if I do a plt.show, it is going to show me the distribution of the error terms. You see, I have a very good model. I really have a very good model, and I am really confident on the model, because this is not exactly a normal kind of a distribution. It looks normal, but it is really close to a normal distribution. You have to agree, the distribution is really close. Okay, it is not perfect. A perfect case would have been what? A perfect case would have been something like this. Let me try and draw this for you. So this part should have been filled, right? This part should have been something like this. So a perfect thing would have been a very good shape kind of a thing. But even the one that we have got over here, this is also not bad, right? So I can clearly say my assumptions are getting met, and I am really happy with what is going on here, right? So this is the first thing I check. Okay, this proves my second assumption. Now to prove my third and fourth assumption, what we are going to do, we are simply going to look at the pattern. Okay, what are we going to look for are the patterns. Before I do that, I'm going to write over here, from above, it is clear that my error terms or residuals are having a very good overall normal distribution. Hence, my regression model can be termed pretty good. Okay, I'm not saying that it is very good, and I will at the end of the day tell you why it is not very good. You should not stop just because one of the assumptions are correct. You should make it far better. Okay, we will come to that far better thing when we start using some other packages or other libraries in Python, which is actually going to, or the other way of doing this is actually the production way. or actually the right way of doing. We have not done one thing in this analysis, which I'm going to tell you, and then we are going to do that as well, which is ideal condition of doing it. It is called training and testing data. We are going to define these terms, and then we are going to do that as well. So I will never call my model the best. It can never be best. Okay, and I will also tell you the reasons behind it. But as of now, let's go ahead and look at the distribution. So further, let's look into the distribution of the error terms with respect to, okay, the error terms with respect to, or maybe a better way of saying this is the X data or the features data with respect to the error terms, to see the pattern of how the residuals have come into existence. Okay, when we draw this, then I'm going to explain you how it actually is going to help us reduce homoscedasticity. Okay, so all we need to do, plot the pattern, right? Simple. We are going to do a plt dot scatter plot. Okay, simple way. Plt dot scatter, put X as the features. In this case it is X, and Y axis is going to be my residuals, which is RES, and I say plt dot show, and it should show me the pattern. Okay, give it 1 minute. It should be okay. X and Y should be of the same size. Why? X and Y are already of the same size. Why is this giving an error? Let me see. X and Y should be of the same size. Okay, let me see. X dot shape and this dot shape. Okay. That should not be a problem. I think there is some issue over here. It should not have been the case. Let me just try and understand what is going on over here. What have we done? We have added the constant, and yeah. Fine. I think let's not waste time on this. I will be getting back to you on this. There is some problem with the data that we can try to fix. Let's not waste time, and let's go ahead with what we needed to do. I will be getting back to you on this. Okay, my apologies. There is some problem with my code, I believe, in this notebook, because of which it is not giving me the results over here. Let me just hide this. Okay, and then we are going to get back to this. Okay, so let's move on, and then let's try to find out what the next set of actions will be. So what we have done over here is we have created the model. We have got our first model. We have done the residual analysis, and we were also going to look at the pattern, but we got an error, unfortunately. Then now we are going to do the next kind of a modeling. I'm going to call this 5, another modeling method. Okay, why I am saying another modeling method is because now I'm going to explain a very important concept, and that concept is something that we will almost always use while doing production use cases, something which we have not done over here. Okay, give me 1 minute. Yeah, so the basic ideology, and this will be good if I write this down. Okay, this is good. So first of all, I'll just quickly finish this. It is always better to present the client with the findings of the best model in the first couple of slides of the final presentation, and then move on with the justification of the final, just a moment, the final presentation, and then move on with the explanations and EDA outputs. Mostly we would share visualizations, but also in the last slide, we must share our code and data. Okay, fine. 27. The best and most practical, okay, most practical way of, okay, performing the any regression or machine learning task is to firstly take the data and break it, okay, into two parts. One which will be used to create the model, and one which will be used to, okay, one which will be used to test or validate the model. Okay, the former is called training set, while the latter is called testing set. Okay, so I'm simply going to divide the data usually in a 70-30 format. So usually this division is done using a 70-30 format. Okay, so 70% of the data I'll use to train my model, 30% of my data I'll use to test my model. Okay, this is just to ensure that I have a different unseen set of data on which I'm going to validate whether my findings are correct or not. And when I validate, then I'll come over and calculate R square and mean squared errors and all these matrices, all these metrics. That is going to tell me whether the model that I've created is really good or not. Right now, there are simple ways of doing this. So if you want, you can also write a Python code, and you can also do this, but I'm not going to do that because I know that Python has already provided brilliant libraries. So I'm going to go on top, okay, and I'm going to clearly make use of my libraries, the libraries which are usually used for this purpose. And there is one library out of the lot of all the libraries which is actually the best when it comes to doing such kind of operations, and that is sklearn. Okay, this library is called scikit-learn. If you want to do production machine learning implementations, this is one of the best as of date to do. So you can learn about this scikit-learn. If you search in Google, you will get the documentation. Okay, this is a brilliant library and it contains everything you need to do when it comes to machine learning. I'm not talking about reinforcement learning or deep learning or any other branch of AI or ML, but everything else is covered in this library. It is very simple API with only one problem. The problem with scikit-learn, you can understand how it is working only by looking at the documentation, not the code. So your code or the output of the code is always a black box. It is not like stats models where you got the output right in front of your eyes in form of a big table which told you the p value and this value and that value and so on. Scikit-learn does not work in that way. Scikit-learn works in different way because it is production ready. It has APIs. You call a function, you get the prediction output. You call a function, you get the prediction accuracy. You call a function, you get the prediction metrics. Right? But it's not going to give you any summary of what it has actually performed within itself. Okay, that is also a very valid or a practical thing to do, because in case of production system, you are not really doing the analysis. You are actually going to run a pipeline, right? You have already done the analysis earlier. I've done the homework. When the model goes to production, then the scenario will be every day from somewhere this advertising.csv file is getting downloaded, or you have to download it, part of your code, right? You have to extract the data out of a database, right? Then you have to write all the machine learning things. So you make use of the scikit-learn library. You train the machine learning model using 70% of the data, which is my training data. You keep the testing data aside. You test the model. You record the findings of the model, okay, or the accuracy, the metrics of the model in some table in a database.
and then you simply output the model and save the model as an API. Right now, anyone who is trying to find out a value of sales or the units which will be sold based on the budget of TV advertisements, he or she is going to call that API or go to a website which is in the backend calling that API. He or she is going to enter the value of the budget for TV advertisements, and in the output, he or she is going to get the value of items which your model is estimating to be sold. Right? This is kind of an example of a machine learning pipeline running on production. In this case, you really do not need to know the p-value. P-value is something when you're analyzing something. In a production pipeline, you're not analyzing, you are actually delivering. Right? That's why scikit-learn comes into picture, and that's exactly what I'm going to use. In scikit-learn, there are many modules, many packages. I'll start with the very simple thing, model underscore selection from sklearn.model underscore selection, import train test split. Okay, so this method, train test split, is actually going to give me the ability so that I can break down my data into training data and testing data. I'll again start from scratch, create the feature series. So this is X is equal to advertising, and then the variable was TV, right? Then I'm going to create the target series, right? So Y is going to be, let's say, advertising sales, right? Then I'm going to say create the training, create the training and testing sets. So I'm going to write, this syntax is very important, as well as it is really very easy. It is the name of the library, the name of the API was what? Train test split, right? Train, then test, then split. Okay, so X train, X test, right? So for X, create the training set and the test set. For Y, create the training set, then create the test set using train test split. I pass the values X comma Y, right? These are my feature series and the target series. Okay, and I don't say anything, and it is going to split. It is going to take a default value, it's going to split. But what if I would like to mention this? So I can mention train size is equal to 0.7, which means take 70% of my data, put it into training, and then put 30% of my data, put it into testing. Obviously, out of these two variables or out of these two inputs, I'm only going to use one, right? Because if I specify training size, testing size is done, right? Now there is one thing that we may need to do over here that is purely optional. You may want to do this in the production pipelines so that your model doesn't change much. Okay, there's a variable called random state. Okay, random state is how the sampling is done. If let's say in one sample, out of 3, I have selected, let's say Rohi. Okay, in the next sample, in the next sampling, am I going to select Rohi or no? Every time I run this notebook, do I need the same data in training and same data in testing or no? If the answer is yes, if as a data scientist you want that, then you put a value against random state, any random value, 101. Okay, you can read about this in the documentation. You will find detailed information on this. If you're not able to understand, please do let me know and I'll explain it once more. A random state with a value, the variable random state with a value 101 or 42 or 38 or 29 or whatsoever, fixes the sample or the way the sample is going to be created for creating the training set and the testing set. This means every time you run this notebook, you get the same training and testing data, and hence you're going to get the same model output. Your model output will not change, right? In this case, let's keep it a constant. Just for testing, we may want to ignore that as well. Now we have created training set and testing set. How can we verify this? Let's simply write this. We have xtrain, it has these many values. You have x test, it has these many values, right? You have training set, you have testing set. Okay, you can clearly see what is the length of this. I can take a len, I believe this should work, right? It has a 140 and this one has 60. Clearly, 70% of 200 records is 140. That's why training data 140, testing data 60. Okay. We don't have time now. Let's make it a stop here. We're going to continue tomorrow. If you have any questions, please do let me know. Yeah.
Yes,
Thanks all.
Thank you.
Thank you. Good night.